So in the previous segment, we learned about the Savinon-Kirchhoff model of nonlinear elasticity. What I want to do in this segment is just put down a few more models which will give us some idea of the range of types of models available out there, right? In contrast with linear elasticity, where there is a single quadratic model. Okay, so we'll just call this segment right. Further models of nonlinear, I guess I should make it clear that we are talking always about hyperelasticity here. Okay. Okay. So really, if we were to continue from the previous segment, we had example 1 there as the Savinon-Kirchhoff. We have example 2. Okay. So example 2 is the incompressible neo-Hookean right, the incompressible neo-Hookean model. It's an exceedingly simple one, right? And it is one that is parameterized by, it can be parameterized in terms of any of the tensors we've seen, but it's most commonly written as a function of the Wright-Cauchy-Green stretch tensor. Okay? It is the following. It is 1/2 2 mu. Of course, the half and 2 cancel out. I'm just used to writing it in that fashion. It's this quantity, mu times the trace of C minus 3. So this is the incompressible neo-Hookean model, and it works rather well for materials such as polymers. Okay? Okay? And something that I could have said in connection with the Savinon-Kirchhoff model, but that is certainly applicable here too, is that this quantity mu that we have here is again the same Lamé parameter that we had in the example of the Savinon-Kirchhoff model. Either in the context of that model or in the context of this model, mu is also understood to be the shear modulus. Okay. In the case of polymer, in the case of polymer mechanics, mu can be related to the underlying structure of long chain molecules and so on, right? So that development can also be carried out. We are not going to get into it here. Okay, so this is the incompressible neo-Hookean. It can be extended to a compressible form . Okay, and that form is the following. Psi hat, also written as a function of C, is 1/4 lambda, right? Now this is our other Lamé parameter coming back. So we have 1/4 lambda, we have here the determinant of C minus 1 minus 1/2 lambda over 2 plus mu natural log of determinant of C, okay, plus the term coming from the incompressible neo-Hookean, right, which is mu trace C minus 3. All right. The difference between the incompressible neo-Hookean and the compressible neo-Hookean is the fact that the incompressible neo-Hookean stores energy only in terms of deformations that, when we consider in the linear elasticity in the limit of small strains, would be considered to be shearing deformations. Okay? So the incompressible neo-Hookean has no component in there that models the effect of changing the volume of the material. Okay, that's why we call it the incompressible neo-Hookean. Okay, so I should include a comment here saying that incompressible neo-Hookean does not have a contribution from change in volume. Okay, so when the incompressible neo-Hookean is actually implemented in models, it needs to be, you need to add on a constraint, okay, to ensure that the volume does not change. Okay, however, the compressible neo-Hookean does have such a term, right? The compressible neo-Hookean includes volume change, right, through all the determinant C terms. Okay, because remember, determinant C is just determinant of F the whole square. Okay, that's where the volume change comes in. All right. The third model we'll talk about is the so-called quadratic logarithmic model. And this is defined in terms of the principal stretches. Okay, so the way we do it is to say, all right, let's recall the following, right? Remember our stretch tensor U, which admits this spectral decomposition. Correct, where lambda is the lambdas are the principal values of the stretches, or alternately the eigenvalues of U, and the NAs are the corresponding eigenvectors. Okay, so this model operates in terms of those eigenvalues. Okay, and the model has the following form. You can view it as being parameterized by U, all right, and it is written also involving the Lamé parameters. Here we have 1/2 lambda times log of lambda 1, lambda 2, lambda 3 square plus 1/2 2 mu times the log of lambda 1 square plus log of lambda 2 square plus log of lambda 3 square. Okay? That is the quadratic logarithmic model. Now, of course, with any one of these models, we can compute any of the stresses, right? So we just start out with psi in whatever form we like. Right? And because we know the transformations between the stretch tensor U, the right Cauchy-Green tensor C, or the Lagrange strain tensor E, we can always convert one model to any other form, right? We can always change these parametrizations. They're all frame invariant. Okay? And from any of these, we have P equals partial of psi with respect to F. We have S equals partial of any form we like with respect to E, right? And what we saw is what we'd used when we computed the elastic tangent and the stress explicitly was we actually used psi equals psi hat of E. Okay? Once we have these, we have the other stresses as well. We then have tau, which is S F transpose with an F here. Okay? And we have sigma, which is just 1 over determinant of F tau. Okay? All of these can be computed. Right? Also, we are able to compute the material elastic tangent, right? We have C, which is the second derivative of psi in whatever form we like, right? Whatever parametrization we like, it's the second derivative. Okay? Now, if we have a model other than the Savinon-Kirchhoff model, what we are going to see is that this quantity C, the elasticity tangent, in general is nonlinear, right? It's not just nonlinear, it is nonlinear, it is also non-constant. Okay? Right? This thing is non-constant for all models other than Savinon-Kirchhoff. Okay? It's really not that difficult to compute the elasticity tangent for I should say this clearly, right? It's the elasticity tangent. It's really not that difficult to compute the elasticity tangent for the Neo-Hookean models. All right, there are some steps which have to be worked out there, but it's not that difficult to do. The quadratic logarithmic model takes a little more work. Okay, so we'll stop here for this segment then.